Welcome all of you. Yes, in the last two classes we discussed several concepts related to NMR spectroscopy, fundamental concepts, basics which are extremely important to understand NMR. We started with the spin of nucleus, spin, what is a spin, what is spin angular momentum, what is a spin quantum number, what is a magnetic quantum number, what is a magnetic moment, interaction of the magnetic moment with the external magnetic field, how it works, and what is the energy separation, what is the resonating frequency nu, which is equal to gamma into B naught over 2 pi we calculated. We also calculated what is the frequency at which this NMR comes in the electromagnetic spectrum, and we did the classical analogy also we gave, which we call it as Zeeman split, Zeeman effect, Zeeman splitting, which the resonance condition we call it as the Larmor precision frequency, which is nothing but the resonance frequency, which is nothing but the energy separation between these two states. Quantum mechanically what we understand, energy separation which is equated to frequency is nothing but the Larmor precision frequency. This is what we understood. We also calculated what is the resonating frequency for different nuclei in a given magnetic field. We understood what is gamma. We understood what is the sign of gamma, what happens to the sign of gamma if it is positive or negative, how do the nuclear spins start precessing. Depend if this gamma have opposite signs, the nuclear spins will precess in the opposite direction. If the spins with positive gamma rotates in the clockwise direction, precesses in the clockwise direction, nuclear spins with negative gamma precesses in the anti-clockwise direction. This is what we discuss extensively. Now today we also understood something about Boltzman distribution. We will continue the Boltzman distribution and try to understand what is the sensitivity of the detection of NMR signal. It is very important. I told you NMR comes in the low energy, especially in the electromagnetic spectrum. When I saw the energy, I showed you in the last column of this table which I showed, energy was very small, very weak energy, very weak interaction compared to all other spectroscopic technique. That means the sensitivity of detection is very small. We will understand what is its sensitivity now. And again we go by the Boltzmann equation. We have two energy states alpha and beta, which is given like this, and Boltzmann equation is given like this. N beta is equal to n beta or n alpha, spin population ratio is given by e to the power of minus E alpha minus E beta or kT. This is the energy separation, and n alpha and n beta are the population of the spins in the states alpha and beta. That also we know, and the ratio of the populations varies exponentially with the energy difference. According to this equation, this is the ratio of spin population. You see how exponentially it is varying. Now we know we can calculate what is E alpha minus E beta, which is nothing but delta E, and also I know delta E is equal to gamma into B naught over 2 pi, which is equal to nu. I calculated nu is equal to gamma into B naught over 2 pi. That is the resonance condition. Because nu is related to delta E, I know what is delta E. I know I can calculate this thing. What I am going to do is, the Boltzmann constant is very well known. It is a constant, easily available, and at a particular temperature I am going to do the experiment. Let us say temperature I express in Kelvin. These are the parameters I know. I know gamma, I know B naught, I know H, I know 2 pi. I can calculate the energy separation I know, and I know at what temperature I am doing the experiment. Boltzmann constant is also known to me. Now what I am going to do is, we will use these parameters and calculate what happens to the sensitivity. For population, which is governed by the Boltzmann population distribution, according to this equation there are two parameters which are responsible for it. One is energy, which depends upon magnetic field. As the magnetic field linearly increases, delta E separation increases, okay, and temperature is also very important, okay. So now there are two factors, major factors that govern the population difference. One is the magnetic field and other is the temperature. For detection of NMR signal, there must be spin population difference. I told you When I calculate the energy population, I wrote the some two energy states. What are the population in the alpha state and beta states? I said there is little excess of population in the ground state or in the lower energy state, and there is a difference in population. This is essential to see NMR. No population difference means no NMR. With this, now we can calculate the population ratio between two energy states, which again depends upon the magnetic field which is in Tesla. I told you what is the magnetic field. So then delta E is equal to nu into gamma into B naught over 2 pi. So it is linearly varies with the magnetic field. So what we will do is we calculate the delta E for a given magnetic field. Let us say magnetic field is 14 Tesla. I know gamma of the proton. I know what is Boltzman constant. I know what is 2 pi. I just plug in these values for my delta E equation. I gave you delta E equation. Delta is equal to gamma into B naught over 2 pi, I said. Okay. Now delta E turns out to be this value. Okay. Now Kb, Boltzman constant I know is 1.381 into 10 to the power minus 23 kilojoules. At temperature at which I am doing is 298 K. I plug in these values. I know K. I have calculated delta E. I know what is T. Just plug in these values. Calculate n beta over n alpha. This is exponential value. I calculated delta E. I know Kb, Boltzman constant. I know T at which I am doing the experiment. You just plug in these values. This is what you are going to get. The population ratio between two spin states n beta and n alpha turns out to be 0.999904, very close to 1, almost 1. It means this population ratio between two states is nearly equal. There is not much of difference in spin populations, and I could even calculate by plugging the values. For example, for 2 million nuclear spins at a 14 Tesla, just plug in these values for this equation 14 Tesla and I calculate, and population difference turns out to be this value. In the beta state we have this many states, in the alpha state we have this many states, this many spins. What is the difference? Difference is only 96. That means at the temperature where I did the experiment, let us say room temperature, now if I calculate the population difference, it turns out to be 96 among 2 million nuclear spins. Remember, where is 2 million nuclear spins? Where is 96? It is extremely small, almost negligible. That shows the difference in spin population that is to be detected is very, very small. Very small population we have to detect. That is why NMR is highly insensitive technique, very, very insensitive technique. Okay. Now what will happen to the sensitivity when I increase the magnetic field? Let us see this. As I told you, there is an expression in the delta E is equal to linear related to B naught. As B naught increases, the energy separation increases. With energy separation increases, population difference increases. That is what is going to happen. Now I consider two energy states. These are the two energy states, and there is a large population difference because this energy state is larger than this one. The small energy separation, the large energy separation, large population difference, small population difference. So as the magnetic field increases linearly, the energy separation between two states increases. That means population difference increases. When the population difference increases, the sensitivity will increase. So it means higher the magnetic field, higher the sensitivity. Okay? If you want to increase the sensitivity of the magnetic field, sensitivity of the detection of the NMR signal, you have to go to higher and higher magnetic field. Higher the magnetic field, higher the sensitivity. This is what I said in one of the slides earlier in the previous class. Now let us calculate the population difference at different magnetic fields and see what is the sensitivity gain we are going to get. Consider a situation where magnetic field is 0. I take the example of 2 million nuclear spins. When magnetic field is 0, that means there is no separation of energy levels. That means it is a degenerate state. there is no population difference. Now I will increase the magnetic field, make some value 2.35 Tesla, and I calculated the population difference, it turns out to be 16. That is all. See, among 2 million at 2.35 Tesla magnetic field, the population difference is only 16. Go to increase the magnetic field again 3 or 4 times, now it becomes 64. Again increase it to some other value 14 Tesla, you see the population difference now is 96. Again go further, make the magnetic field 18.8 Tesla, calculate the energy separation and the population difference. This population difference is only 130. Remember, you started with 0 Tesla and increase the magnetic field tremendously, even from 2.35 almost we have made it 8 to 10 times larger, but the population difference from 16 became only 130. Not a big number, but still it makes significant contribution. The effect is really significant as far as the detection signal is concerned. As we go ahead, I will show you how when we record the spectrum at different frequency, we will get better sensitivity and better resolution. So this is the magnetic field sensitivity, how it changes with the magnetic field versus sensitivity. At 7 Tesla, resonating frequency is 300, let us consider sensitivity as 1 for my reference as a calculation. I go to magnetic field 3 times larger, sensitivity is 5.2 times more, because the sensitivity goes by B naught to the power of 3 by 2. So if I know the magnetic field, I change the magnetic field to the power of 3 by 2 is the enhancement in the sensitivity. So magnetic field and sensitivity depends on the magnetic field. That is one thing which I have to understand. As I said, the magnetic field sensitivity of the detection depends upon the strength of the magnetic field. Okay. Now what are the other factors that is governing the sensitivity? One is magnetic field, I told you, because the energy separation is larger population difference, more sensitivity, fine. There are other factors. One is temperature, I said, remember n beta by n alpha is e to the power of alpha delta E over kT, K is the Boltzman constant, T is the temperature. Remember in this equation T is in the denominator. Now what happens? Let us put some value T as 0. Let us say I go to the T equal to 0 K. I calculate the population. So now because T is equal to 0, it is n b over n alpha, n beta over n alpha is e to the power of minus infinity, which otherwise is 0. So when n b over n alpha equal to 0, n b equal to 0. That means number of spins in the beta state, higher energy state is 0. What does it mean? It means all the nuclear spins in the alpha state, in the lower energy state. When all the spins are in the lower energy state, what is the advantage? The population difference is very high. That is what is going to happen. Higher the population difference and higher the sensitivity. That means if you go to lowest temperature at 0 K, all the nuclear spins will be in the lower energy state, occupy lower energy state, alpha state. As a consequence, sensitivity will be better. You cannot go to 0 K, but understand one concept, as you keep on lowering the temperature, the population difference become more and more. So sensitivity becomes more and more. That is one concept. Now I will, instead of 0, let us do other trick. What happens if I put temperature infinity? Remember, T is in the denominator. If you put T is equal to infinity, now n beta or n alpha, if you calculate, it turns out to be equal to 1. Now when it becomes 1, then what is going to happen? It will n be equal to n alpha. N alpha is equal to n beta. That means the number of spins in both alpha and beta states are equal. When n alpha is equal to n beta, that means there is no population difference at all, absolutely no difference. As a consequence, you will not see signal, and this is called saturation. Saturation is a condition where the populations in both energy states are exactly equal. So, no signal will be seen. Okay? That is you should understand. So, there are other factors which is responsible for giving better sensitivity. One is gamma. Higher the gamma, higher the sensitivity. As I told you, the nucleus with the highest gamma is the proton among all the stable isotopes. And proton, that is hydrogen, has the highest gamma. I told you, it depends upon the mass of the nucleus. This is the lowest one. No, this is not heavy at all compared to all other elements in the periodic table. So, proton has the highest gamma, but highest sensitivity is because of highest gamma. The proton has highest sensitivity because of highest gamma. Why? Because remember, when you go to higher and higher magnetic field, gamma sensitivity depends upon three more factors. One is magnetic moment, population difference, and coil magnetic flux. These are the three parameters. Interestingly, all these three factors depend upon gamma. That means the sensitivity depends upon gamma into gamma into gamma because of these three parameters. So, it depends upon gamma cube. Sensitivity is linearly depend upon gamma cube because of these three parameters. So, higher the gamma, higher the sensitivity. This is what is the reason why I said proton among all the nuclei in the periodic table has the highest gamma. Let us compare now the sensitivity of proton with other two nuclei with a different gamma. Okay. As I said, proton is the highest one. We will consider this as a standard, as a reference. We will compare the sensitivity of the proton with carbon and nitrogen. We will take the ratio. Of course, all other parameters gets cancelled out because B naught is constant. I am not changing 2 pi, everything get cancelled out. Only gamma is the term which remains. Gamma for the proton is this and gamma for carbon is this, which goes by cube. Now, what is the ratio of proton to carbon gamma? If you calculate, it turns out to be close to 4. Ratio is 4 and 4 cube 64, almost 64. That is why if you look at the proton, it is 64 times more sensitive than carbon, whereas carbon is 64 times less sensitive. It is very difficult to detect carbon compared to proton because of gamma. Now, let us see what happened to nitrogen. Nitrogen has 10 times lower gamma, almost 10 times you see, compared to that of proton. So, 10 cube 1000. So, it is almost 1000 times smaller. Of course, it is a negative magnetic moment, that is a different question, because of nitrogen 14 has negative magnetic moment. So, that is not a point to be understood now, because that comes only for NY and others. But right now sensitivity is 1000 times smaller. Remember, if proton, I can do the experiment of proton in just 1 minute. If I under identical conditions, assuming that everything remains same, no change, I need 64 minutes for carbon, I need 1000 minutes to take the nitrogen spectrum under identical conditions. See the difference? Assuming that number of nuclei, number of nitrogen, everything remains same in a given molecule. So, this is the sensitivity factor coming into the picture. So, carbon 30 is 63 times more less sensitive compared to proton, and nitrogen is 960 times less sensitive compared to proton. And sensitivity also depends upon another parameter called natural abundance. Natural abundance of the NMR active nuclei. For example, proton has 3 isotopes, proton, deuterium and tritium, but incidentally this has 99.98% abundant. Fluorine and phosphorus has 100% abundant, one isotope. And these are the 3 nuclei which are relatively more sensitive for detection. It is easy to detect these nuclei than other nuclei. I tell you why. If you look at carbon 13, its sensitivity is 1.1%. Nitrogen is 0.37. Remember, oxygen is even smaller, 0.037. Imagine, very low abundant. What does it mean? If I take an example of a molecule containing only one carbon, for example, take CHCl3, only one carbon is there in this molecule. Let us say I have 100 molecules in a sample, in a bottle, I have 100 molecules. Then possibility of this CHCl3 having carbon 12 as one of the isotope is 99, because that's abundance is more. 99 molecules will have carbon in its carbon 12 state, whereas only one molecule will have carbon in carbon 13 state. You understand? 100 molecules are there, out of which 99 are in carbon in the carbon 12 state, and only one has carbon in the carbon 13 state. So that is why very difficult to detect. So natural abundance is a very important factor. Now what we will do is we will plug in this factor to calculate the sensitivity of carbon and nitrogen, which we did just now. There we considered only gamma, but now we will also factor in natural abundance, bring in natural abundance as a factor. Now this ratio was known, 19/1, 63 is what we calculated, and if you do that, it turns out to be 5672. Remember, now if I bring natural abundance as a factor, the detection of carbon 13 compared to proton is nearly 5700 times less sensitive. It takes more time. Go to nitrogen, it is 1000 times smaller, this sensitivity is already smaller because of gamma, and now abundance is even smaller. It turns out to be nearly 2,60,000 less sensitive. Nitrogen 15 is even more difficult to see because of its very low natural abundance. See the point, what happens, not only gamma, the natural abundance contributes a lot. So it is very difficult to detect these things as because of its natural abundance. So if you go to the, with this we go to the table of NMR active nuclei. In this table you see different color codes. We have half, spin half, yellow spin 3/2 like that. Varieties of nuclei is there. But in all the periodic table you can see almost every element except this range, all the elements of the periodic table has some nuclear spin. At least one element or one isotope of that element has nuclear spin. That means it is NMR active. That shows every element of the periodic table here can be individually studied by NMR. That means now we understood the ubiquitous nature of NMR. If you take any material, biological, organic or material, it must contain one of these elements. It must contain one of these nuclear spins. So if we can use this, that is the reason why NMR can be used to study everything right from chemistry, biology, pharmacy to even material study, because all these things should contain at least one element of this or one isotope of this element. So now with this we will compare the relative sensitivity of the different nuclei at let us say 250 megahertz. If I consider proton is 100%, fluorine is this one, look at this nuclei. In this range is so difficult to see signal at all, whereas carbon 13 is very small here, phosphorus. So this is a relative comparison. Relative sensitivity, assuming one is 100%, what happens if I want to see nitrogen 15, you may not even see the signal compared to that, because I told you 2,60,000 times it is less sensitive, nitrogen 15. So this is what it is. Now we will understand how to get the resonance, how to induce the resonance. So far we understood nucleus, magnetic moment, everything, energy separation, everything. But we understood what are the things about N and M. We should understand R, what is the resonance. NMR is nuclear magnetic resonance. So far we discussed a lot about nucleus, lot about magnetic moment, etc. We will understand the resonance. How do you induce resonance? See, for inducing resonance you must apply a radio frequency pulse. The radio frequency pulse should be applied at the Larmor frequency, at the resonating frequency. So when I apply radio frequency pulse like this, the nuclear spins which are in the lower energy state go to higher energy state, and the spins in the higher energy state will come to lower energy state. And now what is happening? We are going to detect the signal which is the difference between these two populations. This is what is going to happen. That is why I said we are going to detect the signal which is nothing but the difference in the spin populations. That is why the population difference is very important in seeing the signal. But what is this RF pulse? How do you apply this RF pulse? Where do you get this RF pulse? Of course, we generate the RF pulse with a transmitter, and it is a rectangular pulse, and its power is very small, 50 to 300 watt, and frequency is the normal frequency, and width of the pulse is another important thing. Normally it is 5 to 10 microseconds. Remember, pulse width which you apply for excitation or to induce resonance is only of the order of 5 to 10 microseconds for proton, and for carbon 13 is a little bit more, and of course different nuclei you can calculate what is the pulse. Because why I am using is a 90-degree pulse. I will tell you what when you go ahead further. For a 90-degree pulse for proton, approximately we need 5 to 10 microsecond RF pulse with a power of 50 to 300 watts. Okay. The RF pulse is applied in the form of a short pulse, and then magnetization, what is going to happen is tilted from z axis to xy axis. What is the magnetization? I am going to explain to you now. Right now I have not discussed about magnetization, but when we introduce bulk magnetization and random phase approximation, I will tell you what is bulk magnetization. Till then you understand the magnetization is going to be tilted from z axis to the xy plane. Initially magnetization will be along z axis, and you apply a radio frequency pulse along one axis, let us say x axis here, and you tilt the magnetization to y axis, and here we are going to detect the signal. And this amount of tilting, how much magnetization is tilted, is given by this equation gamma b naught over 2 pi. Gamma b naught is the RF power, Tp is the pulse width, and the angle at which you are going to tilt, theta, is given by this power and width of the pulse. If I have a pulse, let us say 5 microsecond, and tilt it by 90 degree, again it is linear. If I go to instead of 5, I will make it 10 microsecond, I will tilt it by 180 degree. If I make it 15 microsecond, I will tilt it by 270 degree. So magnetization which was here, I can tilt it here, take it here, take it here, take it here. I can make it keep rotating like this. I can make the magnetization keep on rotating. It can dance to the tunes. That is what we do. And this is what happens. The magnetization can be tilted by any angle by varying the pulse width and the power. Initially let us say it is along this axis, I apply radio frequency pulse along y axis, I can bring it to here. Apply 180 pulse, I bring it here. Apply 360 pulse, I take it like this and take it back to z axis. So depending upon the pulse you are going to apply. Always all the three are orthogonal to each other. Remember, x, y and z, all the three are orthogonal to each other. Apply a pulse along x axis, bring the magnetization from z axis to y axis, and you put the detector on the y axis, that is what you are going to detect. So if you apply a 90-degree pulse, you bring the magnetization to by 90 degree from z to x axis. Apply 180 pulse, take it to minus z axis. Apply 360, you will bring it back to z axis. This is what is going to happen. The direction of tilting of the magnetization follows what is called a right hand thumb rule. The direction of the thumb is the axis in which you are going to apply the pulse, and the curly finger tells you the direction in which it is going to be tilted. That is important. So with this, how we apply a 90-degree pulse, how we bring the magnetization to x axis, y axis, we can understand. Simply you have to apply the radio frequency pulse at a particular axis perpendicular to the z axis where the magnetization is there. We have to disturb it. We have to create what is called an equilibrium state, and then the magnetization comes to other axis, y axis. All the three are orthogonal to each other, and then we start detecting the signal. How how it works, everything we have to understand by what is called a random phase approximation, which I am going to explain in the next class. Remember, these are the very important concepts to understand NMR. Rest of course, when we go ahead further, we interpret lot of spectra, analyze spectra, varieties of nuclei, everything, different 1D experiments, 2D experiments, etc. But this is the concept which is very important, you have to understand. So what we discussed today, we discussed lot about varieties of nuclei, how we get the signal, what we are going to see, all those things we discussed quite a bit. How do you induce the resonance, what is the sensitivity of different nuclei compared to proton. Okay, sensitivity depends upon varieties of factor. What happens at t is equal to 0, what happens if at t is equal to infinity, that is a saturation. T equal to 0, all the spins are in the ground state, we have maximum sensitivity. As the magnetic field increases, population energy separation becomes larger and larger. Larger the energy separation, larger the population difference. Larger the population difference, higher the sensitivity. All these things we understood. Sensitivity depend upon 3 factors like magnetic flux and how much and gamma. Gamma is, it depends upon gamma cube. The ratio of the gamma between proton and carbon is 4. So, gamma cube is 64. So, 64 times is much smaller. Sensitivity of carbon is 64 times smaller than that of proton. If you factor into account the natural abundance, it is 6400 times, 64 into 100 approximately, 6000 times 400 times smaller. If you go to nitrogen, 10 times smaller gamma, so gamma cube is 1000. If you take sensitivity factor into account, we show that sensitivity of nitrogen 15 is nearly 2.6 lakhs times smaller than that of proton. All these things we understood. And we understood how do we induce the resonance by applying a radio frequency pulse in a direction perpendicular to the magnetic field. And the population difference is what we are going to see. The spins undergo transition from alpha to beta state and beta to alpha state, etc. This is what we understood, and after that this is just basically the concept. But the magnet, if we have to understand NMR resonance, it is just not population undergoing alpha to beta, beta to alpha states, etc. We have to understand by what term what is called bulk magnetization, how it will the bulk magnetization by applying RF pulse, because NMR spectroscopy is a coherence spectroscopy. So, we are going to detect the coherence to detect the signal. So, this we will explain in the next class, and then we understand a little bit of selection rules, everything, and then we go into parameters which are responsible to give rise to NMR signals, etc. later. So, I am going to stop it here. Thank you very much. We will see in the next class.